Welcome everyone to the UK Metamaterials Network webinar series on artificial intelligence. So today we have the great pleasure to welcome Dr. Gareth Conduit from University of Cambridge and the company Intellegens. And Gareth is going to talk on the modern day blacksmith. So Gareth, the floor is yours.
No, thank you very much, Bryn, Sebastian, for inviting me along this afternoon to allow me to share with you some of the work we're doing on applying machine learning to real-life experimental systems. So one big challenge that we are going to face to start off, we've all heard of the progress of machine learning has been making in the media. We've very recently learned about ChatGPT and the progress it's making. But one big problem that we're going to have in applying those machine learning methods to some of the real life data that we as scientists face is that our data tends to be quite dirty. It's going to be dirty, firstly, because typically there are lots of properties of materials and chemicals that we need to understand and get right, but not all of them will be measured for every material in our training data set. So therefore our data sets are inherently sparse, there's lots of missing values, and this is going to hugely complicate the application of machine learning, because after all, machine learning is just a mathematical formula that needs every input to give an output. Secondly, we're also going to face the fact that our data typically comes from experiments, and experiments have uncertainty on them, leading to noise in the data. And we're going to need a machine learning method that will be robust and, dare I say, could even exploit that. And today I'm going to present to you how we have attempted to work to overcome this problem of sparse and noisy data. And I'm going to show you three different ways that we've been able to do that. The first topic is going to be to notice that many material properties are correlated to each other. So for example, a material that is a good electrical conductor is often also a good thermal conductor. And so can we use the information from one property to predict another? The second approach is going to be to ask, can we interrogate the machine learning to tell us what is the next best place to perform an experiment so that we can learn more about the system, that we can put that new experimental measurement into our training database, train up our machine learning, and then get a better model in the future. And the third is going to be to see how we can actually harness the noise in the experimental data to understand the uncertainty in our predictions, and thereby not design the material that we expect to have the best property, but the one that we think is the highest probability of performing well. And we're going to see how effective that can be in delivering better predictions, better designs to the ultimate end user. And we're first going to kick off by having a look at how we can exploit property-property relationships. Oh no, sorry, before that, of course, first is a quick outline of how our the basic viewpoint of how our machine learning framework is set up, where the basic problem is always going to have the same pattern, that we're going to start off on the left with the ingredients of the material or chemical. So in this case for material, it's going to be the concentrations of all the different elements that we might put into the material, and also the processing parameters, so how long do we hold it at what temperature in order to create the appropriate microstructure. So we've got here all of the knobs and dials that one would turn in a factory, and we're going to put those into our machine learning black box at the center. This is the thing that's got the mathematical gubbins in it, and out on the right, it will then predict for us the properties of the material we're interested in. Here I've got the number of defects, cracks and pores formed in the material. We have the fatigue life, and we also have the strength. Now, the machine learning, unfortunately, won't work like magic. It's going to have to somehow learn about and understand the material. And to do that, it's much like a student at university, that it has to go to the library in order to be able to learn and take advantage of historical information. So in this case, it's going to be a database of all the materials that have been made in the past. We've got a big database of those. We can get it, feed it into the machine learning tool. So in effect, it's a curve fitting tool. It will sort of understand what weights it needs to fit the curve. And then once it has been trained off that historical data, we can take the historical data away. We can then give it a fresh composition and processing parameters that it has never seen before, and it will predict for us what it thinks the properties will be. Now, this is only ever going to be a prediction, but we're fortunate that the machine learning tool can make a prediction maybe just 1 millisecond or so, and at the underlying cost of some fraction of a penny, which is going to be an awful lot quicker and cheaper than doing a real life experiment, which might take upwards of a year to do and cost maybe $10,000. And so getting the prediction from the machine learning can, if used the right way, dramatically shortcut the number of experiments we have to do. And one might, for example, use it to do a screen of all the material space, then identify which possible material has the best possible properties that you can then make and verify in experiment. So that being the big picture, you now go on and have a look at sort of the first way that we can sort of circumvent some of the real difficulties we're going to have in applying this methodology to real life data. And that is to notice that there are material properties are often strongly correlated, and to see how we can exploit this to significantly improve the quality of our predictions. The project that I'm going to use to demonstrate how we did this is one of the early pieces of work that we did with Rolls-Royce, who are interested in making jet engines like the one that we have shown here. Now, Rolls-Royce is always interested in making their jet engines more fuel efficient and more environmentally friendly. And in this project, we were tasked with looking right at the heart of the engine here, which is where the fuel is injected and burned and gives off a lot of energy. So to make the engine efficient, we're going to want to burn the fuel as hot as possible, so we can, by the sort of Carnot cycle physics, extract as much energy, useful work from it as possible. And also we're going to want as complete and clean combustion as possible, so truly make sure all the fuel is burned. And to do that, we can see in the cutaway of the components here that it's really intricately shaped to get the perfect fuel-air mixture. But this component shown here was made in very traditional manufacturing techniques, a combination of casting and fabrication. But Rolls-Royce want to turn to a new manufacturing technique, which is 3D printing or additive manufacturing for alloys, which promises to be able to print an even more intricately and delicately shaped component to make the engine even more efficient. Now, the additive manufacturing process that Rolls-Royce are interested here is something called direct laser deposition, which we can see here in the schematic. We can see that coming out of the nozzle here is fired these 3 jets of powdered metal, which are being fired down onto the component here, which is being printed. And down through the center of this nozzle, here's a laser beam. Of course, it's outside the visible spectrum, so you can't see it, but that's what's melting the powder onto the component, and then the print head of the nozzle goes back and forth to print the component. Now, we can see already that this additive manufacturing looks like a violent process, and it's actually even worse than that, because we are locally melting the powder onto the material. So we locally heat it to get local thermal expansion and contraction, and that tends to lead to a lot of cracks, defects, and pores being formed in this material. And so the challenge is to try to propose a new metal alloy that's going to be both good for 3D printing, so we'll be able to print it without making these cracks, and at the same time we'll also have many other good properties to be able to sustain the very high temperature conditions in the engine. So we thought we'd turn to machine learning to give this a go, and we've got here a little cartoon of how we would train the machine learning model just to predict the one property for now, the number of defects formed in the alloy, where we go from the left composition through the machine learning tool to predict the defects. But we can see there's going to be an immediate problem common to many experimental driven R&D projects, which is that we haven't really done much 3D printing on this new family of alloys in the past, and hence why we're trying to discover new materials that are good for it. In fact, when we did this project, there were just 10 experimental results available for how well 10 different alloys performed in 3D printing, which just doesn't sound like very much to do machine learning. And in fact, the problem's even more stark when we consider that the input parameter space is going to comprise the concentrations of about 20 different metallic elements that one might consider putting into this alloy, and a further 10 variables to describe the processing parameters, like how much power do we put through the laser and how quickly do we scan it back and forth. So overall, we've got a 30-dimensional space, and we know just from school level maths that in order to specify those 30 numbers, we're going to need at least 30 pieces of data, and therefore 10 is just clearly not enough. And so it sounds like we're already sunk here, that we're not going to be able to do this just because we don't have enough data. And so this is really the sort of almost exemplar sparse data system, but we're going to see how we can now use our sort of materials and chemical intuition to overcome this sparsity. And the way that we are going to do that is to, if I get out of the way, is to notice that there's another material process that's similar to 3D printing. That in 3D printing, direct laser deposition, on the left, we notice that we are melting the material locally using a laser beam, whereas over here on the right, we are welding, and in welding, we melt the material locally, but with electricity. So therefore, we would hope that if a material is good at welding and doesn't form cracks and defects on welding, then there's a good chance that it would also be good for direct laser deposition. And we're also fortunate that welding is an older process. It's been tried on many other alloys, so we've got a lot more data for it. So one might conjecture perhaps we could just look through the family of materials good for welding, and then there's a decent chance that'd also be good for 3D printing. And so that's in effect what we're going to do. We're going to first go off and take all of our welding data. We've got about 1,000 entries for it, and use that to train a machine learning model that will go from the composition and processing parameters across to how many defects are formed on welding. Then once we train this model, we've got a tool that can predict how weldable an alloy is. We can then, on top of that, train a second machine learning model that will take in how weldable the alloy is and tell us how good it would be for 3D printing. And if our intuition is correct, then the relationship between weldability and 3D printability should be almost one-to-one. It should be close to a straight line. And we know that we only need 2 data points in order to specify a straight line. We need 3 collinear data points to know that it is a straight line. And so 10 data points almost suddenly seems like a luxury. And therefore, we now have a credible way of predicting ability for 3D printing. So in summary, we're going to take composition, pass through the machine learning method to predict weldability, then take that through a second machine learning model to predict 3D printing. And so we've stacked 2 interpolating machine learning models that together give, in effect, one super machine learning model that performs what appeared to be a mathematically impossible extrapolation. And so this is almost going to work for us like magic. And so that's one example of a way that we can exploit relationships between different material properties to greatly enhance, in this case, even make it feasible to make predictions about the 3D printability at all. And so that's just one example of this. There's going to be lots of other properties that we're going to take advantage of, correlations in between, for example, hardness and strength, the underlying phase behavior, what precipitates are formed in the material, and many of the sort of physical strength-like properties, electrical conductivity, thermal conductivity, and so on. But with that in place, the next stage is to go and talk now to our experimental collaborators, the engineers that are actually going to be making the engine, and ask them what properties they actually want. And I've got here listed all the properties, the targets that we need to fulfill. Up at the top, the one that's always the most important, which is the cost, that it's vital for the alloy to be cheap enough to be commercially viable. And the next one down, the density, that we need the alloy to be light enough that the plane could actually take off from the ground. Highlighted here is the number of defects formed in the alloy on 3D printing. So that's how good it would be for 3D printing. And then down the bottom here, we've got lots of properties about the strength of the material at the high temperatures in the engine. And so these are just the targets that Rolls-Royce are interested in. They're also off the bottom of the slide a whole long list of other properties that Rolls-Royce don't care about, but are going to be acting as a proxy for some of these. So for example, the weldability is another one off the bottom of the slide. So we're to go off, collect data for all of these properties from various sources, collate it together, train our machine learning tool. It automatically understands the relationships between properties and exploits them if it can understand that will be statistically beneficial. Train the machine learning model, and then we can get it to make predictions about once a millisecond, and we can get it to explore the broad range of different material compositions until it finds the one that will fulfill these targets. And this is what it came up with. We've got here the composition. It's got 10 different elements in it. It's basically a nickel alloy with some other additives. And we can immediately see that it's a very complex alloy. Typical alloys have maybe up to 6 elements or so, and the number is just limited by the number of permutations that one can consider in a typical experimental driven campaign. But here we're looking for the alloy in a computer, so we can do it very quickly and explore more complex alloys, and that immediately gives us the opportunity to go off into virgin territory and explore something not previously possible. And also for those alloy enthusiasts, we'll also recognize that it's a high entropy alloy, and it's just a basic property of these, that the more elements you put in, the higher the entropy and the better the properties at high temperature. Now, we not only specify the alloy composition, we also specify the processing parameters. If I get out of the way, we've got in the end here 2 of the processing parameters, the exposure, which is a bit like sort of how much oomph do you put through the laser beam, and also post-processing heat treatment. There's several other processing parameters that are off the end of the slide here. But once we design the alloys, my work is done, and we can now pass the design over to our experimental collaborators at the Rolls-Royce University Technology Centre, the University of Cambridge, a group led by Professor Howard Stone, who could go off, make the alloy and test its properties. So the first set of properties we want to do is the phase behavior. So it's on the list of the targets here, it's these 3, and this tells us what different sort of crystal structures form in the alloy, where we kind of know for a nickel superalloy what we expect to see. So those are the targets, and a way to test these is you look at the alloy under a microscope, and this is what it looks like. We can immediately see that it's got 2 phases in it. It's got the background grey phase, and within that there are these black sort of precipitates, blobs that are forming, and they're critical to give the alloy its strength. So we could go off, measure the density of these, measure the size of these, etc., and show that we have understood the thermodynamics well, and it looks like the kind of alloy we would hope for. The next thing that we need to do is look at this much more carefully under is to look at it and see how many defects are formed, how many cracks are there. Superficially, it doesn't look like there's any gaping cracks through the material, but if we look much more closely, I've tried to highlight them in these orange circles, we can see these little sort of suspicious areas where it looks like a small defect may have been formed. But we can go off and measure these much more formally to see if we can hit the target of fewer than 0.15% of the material being defects. And I actually got a graph here of the number of defects on the y-axis as a function of one of the processing parameters, this exposure parameter, sort of laser power, on the x-axis. So we want few defects. We're going to want to be in that bottom shaded gray area of the plot. And we can see that at the exposure parameter that we recommended, which is highlighted by this orange arrow of 0.8, that yes, indeed, the experimental measurement, the magenta point, does have few defects, that the alloy has actually worked and we can print it with a relatively small number of pores being formed. However, we can see that over on the left, if we had a smaller exposure parameter, that the alloy unfortunately wouldn't have worked, that we see here that we would have formed too many defects. And so this shows us that firstly, we've been able to print a good alloy and that we've got a good understanding of the effect of that exposure parameter. So that's just a couple of the properties that we've been measured. We measured several more of the alloy to check they work. And if you're interested, you can read more about them in this peer-reviewed paper. So that's the first project that we did, where we were demonstrating the ability to exploit, or the benefits of exploiting relationships between different material properties. However, there's so much more that we can do using machine learning. And next I want to take a twist, move in a different direction, and recall that often the experimental data we train from has inevitable experimental uncertainty on that, and discuss how we can actually exploit that in a design of experiments a program to try to ask where can we perform more experiments to learn more about the system. And our setting for this is a very cool project that we did firstly with the Advanced Manufacturing Research Centre at the University of Sheffield and several other collaborators, Boeing Aerospace, and then behind me we've got General Electric Additive, and behind me on this other side we got a metal powder company called Constellium. And the idea here is to ask what would happen if you'd have just bought yourself a shiny new 3D printing machine, in this case from General Electric, like the one that I've shown here. Then you'll find that you can't just turn it on and start printing, that it's extremely sort of complex, and you've got to very carefully set it up for the particular powder, for the system that you have. And this is going to be a time-consuming, expensive process. And so we want to ask, can we use machine learning to help us set it up quicker? Can we use machine learning to guide us? What experiments do we need to do in the machine in order to be able to understand how it works as quickly as possible? And so if I just skip a couple of the slides here to go on to the campaign that we are going to run, the basic idea is that we're going to kick off at the top here by performing a few experiments which are somehow predetermined, perhaps the ones that you've sort of done on different machines in the past, in order that we can build up an initial small database to train a minimal machine learning model. Then once we've got that machine learning model trained, we're then going to want to interrogate it to ask where should we perform some additional experiments in order to understand the system better, so we can train a better machine learning model in the future. And to see how we can do that, I've got here a sort of a simple graph of y versus x, where x is like the input, it might be the amount of power in the laser, and y is a measurement of how well the quality of the print perhaps. And in grey are all of our already taken experimental results. Then we take those, we train our machine learning model on it, which gives an expected prediction of the dark blue line that goes up the center, where we can see that it's basically, I've set it up here to be a straight line, except for this grey point around here, which looks like it might be an outlier, perhaps scientifically interesting, when the machine learning model is kind of hedging its bets between the straight line and going up here. But crucially, some machine learning methods are able to not only make the prediction of the dark blue curve, but also tell you the uncertainty on that, which is the light blue curves here. And this uncertainty can have multiple sources. Over on the left-hand side here, we see that our data happens to have some experimental uncertainty on it. It's a bit scattered. The dark blue line is cleverly not followed all the points, but taken a bit of an average through them. And there the light blue curve is going to be like the uncertainty, the standard deviation in the mean, so the sigma over square root of n. Now here in the middle, we've got this outlier, where the machine learning method is a bit suspicious and not quite sure what's going on, and that's reflecting the uncertainty that it knows it might be a straight line, and so that's this bottom light blue curve here, or it knows it might be all the way up here, which is this upper light blue curve, and it's not quite sure. In this region here, there's very little uncertainty because our points are dead arrow straight. And out here, we just don't have any experimental data at all. It's for a set of input parameters that we've never tried before, as the machine learning method in this case has opted to do linear extrapolation up here, but it is honest and frankly doesn't know where the curve goes at all, and it knows where it might curve all the way down here, it might go all the way up here, and so it's rather hedging its bets. So if we then are faced with this, we can see where should we perform an additional experiment. We see that our human intuition would tell us, well, why don't you perform it all the way over here, somewhere on the right-hand side? Because that would immediately tell us if the curve goes down here, up here, or wherever it goes. Or here would be another good place, because it might be that it would confirm for us that this is an outlier and the point would be down here, or maybe it would show that it's actually a really scientifically interesting point and pick out some phase transition. Or perhaps we could also be worth doing a few more points over here, because then we'd have a few more points to take a better average through them and reduce this uncertainty. But in this instance, the preference for taking the additional data always seems to be correlated with where is the uncertainty large. And so you'd want to kick off by doing some more experiments up here, then down here. And so this is exactly how we can use our machine learning method to tell us where to look next. Where is the uncertainty largest? That's a good place to do some more experiments. So indeed, we can do that. We can do those experiments. We can get the additional data. We can then put that back into our database, train a new machine learning model in the presence of this more data. And then we could either straight use it to do some designing, or perhaps you could cycle around again and ask, where should I perform the next experiment to improve my understanding of the system. Now, one additional complexity we're going to have here is that in 3D printing, you can do more than one experiment simultaneously. Indeed, actually, as shown here on the left, this is a set of samples that they printed that they're able to perform what is of order, I think it's 64 experiments or more simultaneously here. And therefore, we want to propose that number simultaneously of where should we do those. And so we're going to need a really clever machine learning method that's able to do that, that's able to propose one experiment in the deep extrapolatory region, and then when proposing the next, to not propose the same thing because we'll learn the same information, but somehow to be pushed away from there and go somewhere else as where to look next. And so one needs to set up the machine, the design of experiments to do that. And so all the samples here are each printed using the same powder, but with different processing parameters. Another twist that we need to think about is that there's also a benefit in thinking about all of the different properties we need to get right. Here, I've spoken about just one property, but there's going to be other properties that we're going to need to sort of understand as well. And it might be it's worth doing an experiment where all of the properties are quite poorly understood, rather than somewhere where one property is terribly understood and all the others have excellent understanding. We can do that. We can set up a design of experiments framework to do that, to understand the advantages and disadvantages of different experiments, go off, get this data, and then we can actually go and test the performance of our machine learning tool. So we've got here quite a classic plot that we do. It's got on the y-axis the predictions from our machine learning tool, and on the x-axis the actual experimentally measured value. So in short, this is supposed to be, if the machine learning was perfect, a straight line at 40 with all the points aligned 45 degrees. Now we can see that down the bottom left, which happened to be an area where we weren't actually that interested, that our machine learning predictions tend to have large uncertainties and they're not necessarily that accurate. But up in the top right, which is the area, the type of properties we're actually interested in, that here the machine learning method is performing well, and we're able to get some very high quality predictions. And indeed, so excited were we about this that I got here a quote from Dr. Giranek, one of the researchers over at Boeing, who is really sort of delighted with the outcomes of this project. So we're now working further with them on the sort of use, the rollout of machine learning to drive forward the adoption of additive manufacturing in Boeing and some other organizations. So that's the second use of uncertainty, where we were trying to look where is the uncertainty in the machine learning the largest, because that will be a good place to get additional data to learn more about the system. Now, the third use of uncertainty that I'd like to highlight is to actually go in completely the opposite direction. That is to now ask, we've got our machine learning tool and we're allowed to make one final prediction design for the company, the experimentalist, that they're going to go off and make, and we've got to get the right one, because if we don't, they're not going to talk to us or work with us again. And so in this instance, we're going to have a completely opposite philosophy. Rather than maximizing the uncertainty, we're instead going to try to minimize the uncertainty. Now, I'm also going to take a different change in tack here. Our previous projects were talking about sort of alloys and 3D printing, but this time I want to talk about some chemistry work that we did, in fact, pharmaceutical work in designing new drugs. So in this project, we entered the open source malaria drug competition, which is run by Professor Todd at UCL, which is run as a challenge to the machine learning field to be able to test out and design, test out their machine learning methods, design new drugs to combat malaria. So this competition is going to be run in two parts. The first was testing many different organizations' machine learning methods against benchmark data sets. And the second, even more exciting bit, is to design a new drug and then test it to see if it would work. Before doing that, I thought I'd just show a quick schematic of some ideas about how drugs work in the human body. Where I've got here an example of one possible drug molecule, which is adrenaline, which when we inject it in the human body, we transit along that first arrow and see how it affects the behavior of proteins in the human body. So for some proteins, it might increase its activity, and for others maybe decrease, and others leave the proteins unchanged. Then, once you change the activity of certain proteins in the body, this can go on and have an effect, a physiological effect on the subject. Like, for example, in this instance, it will make you run faster. So in order to design new drugs, there's going to be a two-step process. We're going to need to understand how drugs affect proteins. And then secondly, we're going to need to understand how proteins affect sort of the response of the person. Now, in this project, we're going to be completely focused on the first part of the process. We're going to not worry at all about the second part, that somebody else has already worked out what proteins we need to change the activity of and which ones we need to leave untouched. And we're going to worry about how a drug affects all of, it's about 10,000 proteins in the human body. So to do that, we're going to turn again to machine learning. It's going to be similar to before, except this time rather than inputting concentrations of metallic elements, we're going to have which atoms are in the drug and lots of descriptors for where they are, like how many alcohol groups do you have and how many benzene rings do you have and aldehydes, etc. And then the output, rather than being the strength of the material, is going to be the activity value of the proteins, which there's about 10,000 that we will need to be able to predict. Now, that's a lot. We're using various of open source databases that are available to train our machine learning. And we could also note that that data is typically very sparse. It's typically about 0.05% complete. And so we're fortunate we've got a machine learning method that can exploit correlations. And it's also the case that the correlations between proteins tend to be extremely strong. And that's exactly the kind of correlations that we are good at picking up on. But once we've done that, we can then, I want to highlight how we can actually use our machine learning tool. So I've got here a graph of the activity level on the y-axis of just one, perhaps the critical protein in the human body. And on the x-axis, I've got here 4 different candidate drugs. I'll get out of the way, drugs 1 through 4. And our machine learning method has gone and predicted for us the expected activity for each of these drugs. So that's going to be like here, the central value here. But also our machine learning method is good at predicting uncertainty. So we know for each of these, the uncertainty due to the inaccuracy of our machine learning model. And we can see, for example, drug 3 has a large uncertainty, which might be because we're dramatically extrapolating to some completely new kind of chemical space that's never been considered. Whereas drug 4 over here has got very small uncertainty, which could be because it's a drug that's been made before, and so the machine learning method already knows about it. Now, I want to overlay these with the actual measured values of these activities. So again, the machine learning model didn't have access to these activities when it was trained. Instead, these activities, you can imagine, it's a retrospective, they've been measured after the fact. Now, of course, we don't expect these to line up perfectly with our machine learning predictions, but if we've done a good job with the uncertainties, then we do expect that typically the orange true value should be within about the 1 standard deviation of the machine learning prediction. And here in this cartoon, we can see that is the case. Then when we go off and want to measure the accuracy of our machine learning method, which could be, for example, by measuring the mean square error, you go off, you measure the length of all those grey arrows between the expected value and the true one, and you square all those lengths and then add them all up to get an overall error. Now we can see the bulk of this error up in the top right going to come from the length of the largest arrow squared, that of drug number 3. And then this is where we look at it and we can think of a really cunning and devious plan here, which is I kind of knew before the fact that that grey arrow was going to be long because the standard deviation that I predicted before I knew the true value was also long. And so I can be really perhaps even naughty and say, well, perhaps because I knew that was going to be the worst, it could be that my machine learning model would just refuse to predict it entirely and will cross it off. And then suddenly my error for my remaining drugs becomes smaller. And then having done that once, why stop there? Why don't I also cross off the next longest one, drug 1, and the next longest, drug 3? And then I'm only left with drug 4, which I knew before we even tested it would probably be the best one. And then my mean square error for my predictions is going to be really small. And so this seems like a really fantastic idea to sort of artificially boost the accuracy of our machine learning tool. Now, the flip side of this, of course, is that a data scientist, someone training machine learning models, will say, oi, you're cheating, that you were supposed to be predicting everything. You had everything in your validation set, all those orange points, and you're not bothered to predict them all. And so you haven't actually made more accurate predictions. But nevertheless, if I ignore them for a moment, we can plot here a graph of accuracy versus amount of data that we're predicting. So the accuracy here, we're using a measure often using drug space, the coefficient of determination, where up at the top now means very accurate results. In fact, r squared of 1 is perfect, and r squared of a half is not great, but r squared would range typically down to 0, which is the most corresponds to a naive prediction of the average. And on the x-axis here, we've got the amount of data we're predicting, whereas if we're being sort of good and honest and predicting everything in the validation set, we'd be over here, on the right-hand side of the graph, predicting 100% of the data. And we can see the r squared isn't so great. But if we accidentally, or if we cunningly throw away the predictions that aren't so good, we can see this curve go inexorably up to make very accurate predictions. And r squared of something up beyond about 0.7 would be regarded often as good enough in order to consider using this to replace experiments, and beyond 0.9 is perfection. And so we can see that we're doing a really good job of the uncertainties here, because this curve's going up. If we were making terrible predictions of the uncertainties, in fact, the opposite of what they should be, this curve would actually go down if we throw away the good results first. And so this seems great, but of course, we're liable to being accused that you're just cheating in your data science. You're not actually training some machine learning method that's making better predictions than other methodologies. However, at this point, we would claim that's actually sort of missing the whole point of what we're trying to do here, that the machine learning is just a tool that we should be using alongside the discovery process, and the ultimate end user, in this case, the drug user. If I went down to the pharmacist and was buying a drug, I don't care what the manufacturer's curve of accuracy looks like. What I actually care about is whether the drug works. And we can think back to perhaps the COVID pandemic, when there was an absolute desperate race in order to discover the first vaccine, that ultimately lots of vaccines came out on the market. We got here 4 of the leaders that were approved in the UK. And of course, they all work in entirely different ways, completely different vaccines. But if I were a drug company, I don't, of course, need a machine learning method. I don't need to discover all of these. What's more important to me as a drug discovery is to be the first to discover one of them and be the first to get it out to market, which in this case was Pfizer, and it has significantly boosted the long-term prospects for that company. And so in applying these machine learning methods, we can often realize that when we're designing something, often there's lots of possible solutions out there, and our job is only to find one of them, but it's better to find the one we're really confident in, so you can put all of your resource behind it, rather than having lots of possibilities and having to check them all. And so that means that actually this trick of throwing away results we're less certain about is really powerful, because provided there's lots of solutions out there and at least one of them lives on the left-hand side of this curve, then we're on to an absolute winner, and we're going to definitely be trying to design things hard over on the left where we're really confident that they're going to work. And so that's exactly what we did in the open source malaria drug competition. We went off, proposed a molecule. This is the one that we proposed. Then Professor Todd and his group went off, synthesized it, tested its activity, and it worked. And so that's absolutely fantastic. Whereas there are 3 other organizations as finalists in this competition. They proposed these other drug molecules, which ultimately, when tested, unfortunately didn't work. And then we can do a retrospective and see that's almost certainly because we predicted these also as having good properties, but they were always in deep extrapolatory regions of the curve, where they're extrapolating way beyond the range of the data, where the properties were shooting up and the uncertainties were becoming massive. And because we had a really tight handle on our uncertainties, we were able to steer away from these and focus on the one that would actually we were confident would work in real life. And so that's a really a really good demonstrator of the benefits of having a really good grip in your uncertainties and then exploiting them in order to make the design things that got the highest probability of working. So I've just shown you today 3 different projects we've been involved in, but our underlying methodology is completely generic and doing this sparse, noisy data. And we've been involved in lots of other design projects. I don't really have time to go through them, but I just highlight here some of the ones that have actually led to published papers. Johnson Matthey, NASA, several more with Rolls-Royce, Antis Granta, these were all metals. Then in other chemical space, several with various drugs companies, batteries, BP are doing lubricants for electric vehicles, and a cool project up in the top right with international flavors and fragrances on replacing the qualitative measure of how sort of sweet smelling is a perfume. As these are just the ones that we've published, there's also, of course, many other projects that we're not able to got a rather confidential commercial clauses surrounding them. But in summary, I've shown today how we can set up machine learning tools that are really fine-tuned to work well on the typical experimental data that we encounter. I showed you 3 tricks, how we can exploit relationships between different material properties in order to boost the accuracy of our predictions. I showed you how we can take advantage of our knowledge of uncertainty and where it is large to do a very effective design of experiments. And also the flip side, how we can exploit where uncertainty is small to be able to design formulations that have got the highest probability of working in order to boost the success rate. And of course, as Sebastian mentioned at the beginning, this work was initially done at the University of Cambridge, but since then, to really maximize the commercial impact of it, we've co-founded a startup, Intellegens, that's now taken it to market as a software tool licensed to their customers. So with that, I'd like to thank you all for your attention and hope there's a couple of minutes for questions.
Super, guys. I mean, inspirational talk. Fantastic.